Good morning. Now that we've done just a brief review of what we learned about the atom before fall break, we're going to delve a little more deeply into quantum theory. And we'll have talked just a little bit about Bohr's model, but we're going to start by looking at Bohr's model one more time and then talking about how that segues into the quantum model of the atom. So let me share my screen and get back to the slides. So you may remember before break, we did the Geiser tube apparatus. And basically that was vacuum tubes that had electrodes in each end. And then in the vacuum tube was a specific gas. And when we electrified it, we would see that the gas gave off a specific color of light. Furthermore, when we looked at that light through diffraction grating in class, and then at home, you guys used that periodic table that showed you the emission spectra, we were able to see that those colors of light broke down into discrete bars of light. Those are the wavelengths that are being kicked out by the electrons after they've absorbed energy. So the whole idea of electrons absorbing energy, jumping up to higher energy levels, and then giving off light as they drop back down was originated by Bohr. At least he was one of the major proponents of proposing that atoms had energy levels. And so when he first drew a model of what he thought the atom would look like, it looked a little more like this. Let me go to a full screen here so you can see. So he said, yes, there is a tiny nucleus with protons and neutrons, tiny comparatively speaking, and then there are energy levels. And he said the first energy level holds 2 electrons, and then the second energy level holds 8 electrons. And then the third holds 18. And then the one outside of that holds 32. I'm not going to draw those 32. But, so these little circles would represent electrons, and he spread them out because electrons are negative and they repel each other. This last level and levels there on out would hold 32. So if you look at this model, it kind of reminds you of planets going around the sun. So this was called the solar system model, just as a shorthand way to describe it. What we know now, though, is that electrons don't like go in these nice clean circles around that nucleus. Instead, what they do is they occupy specific spaces, and we call those spaces electron clouds or orbitals. So let's go back to the slides for a second. And what you'll see next is just a brief summation of what I said. Bohr's model was good. It acknowledged that there were energy levels, but what we know now is that electrons actually reside in orbitals. And scientists have described those orbitals as 4 different types. The s orbital, p orbitals, d orbitals, and f orbitals. By the way, right now this is all going to sound foreign, but just watch this and give it a second to absorb, and you'll see that what we actually do with it is not that complicated. So what do we mean by orbitals? Well, first of all, what I'd like you to do is I would like you to copy this into your composition book. We now know that electrons actually reside in orbitals on the energy levels. And so if you could pause this video for a second and add this into your notes, there's one s orbital and it holds 2 electrons. There's 3 p orbitals. They hold a total of 6 electrons. Take a second and copy that, and then we'll move on from there. So I'm assuming that you've copied that and you're now back for a little more information. So what I'm going to do is I'm going to take a second and show you a video, it's really short, that kind of represents what these electrons look like. So let me take this back. So here is our video that we're going to watch real quickly. Let me see if I can get this out of the way. Notice before we start that they're representing the atom three-dimensionally. And they're doing that using an X, Y, and Z axis. We're used to X and Y, you know, that's two-dimensional, but atoms aren't two-dimensional. They're not flat, they're three-dimensional. So that's why we have these three axes. So let's go ahead and start this. Excuse the music. So the first orbital is in the center where those three axes intersect, and it's spherical. There's one s orbital. The next orbitals are the p orbitals, and you'll see that they look, you can see they're by their color. There's three different ones, and they actually kind of have these lobes. I had a student once describe them as peanuts. The third type of orbital is the d orbitals, and there's 5 different ones. There's the first one. Here's what the second orbital looks like. There's our third orbital, the fourth orbital, and then the kind of psychedelic 5th orbital. So this video has shown them to you separately. Now they're going to show you these overlapped. They have not included the f orbitals. So there's our s, our 3 p orbitals, and then all of the d orbitals. So you'll notice now that they take up most of the three-dimensional space of that atom to explain where electrons can be found. So going back to what we were talking about, we said that there's one s orbital. You saw that, that was the sphere. There are 3 p orbitals, and those were the ones that kind of looked like 2 lobes along each of the 3 axes. So there was one around each of the 3 axes. The d orbitals get really wonky shaped, and this illustration I showed you didn't even show you the f orbitals. So let's watch that one more time, just so we can kind of get a sense of what we're looking at. One more time, just to kind of make it more visual. Oops, sorry about that. Here we go. So once again, the s orbital where the 3 axes intersect. The p orbitals are going to come out along all 3 of those axes, kind of as these 2-lobed peanuts, if you will. You can see the 3 shades: yellow, medium orange, and dark orange. Here's our first d orbital. It fills in the space between the x and z axes. The second is the space between the x and y axes. The third is between the y and z orbitals. Then it starts getting too complex to describe. One that looks almost like an atom bomb cloud reflected. Now they'll show you all of them overlapped. S, P, the 5 d orbitals, and they are most of the space now. The last one they're going to add the last d. So where do we go from there? What are you actually going to have to do with this information? Well, you're not going to have to draw those orbitals. What we actually do with this is we use these orbitals to describe the electron arrangements of different atoms. As we already mentioned, there's one s orbital that holds 2 electrons on a given level. There can be up to 3 p orbitals that can hold 2 electrons in each orbital for a total of 6. 5 hold a total of 10, 7 hold a total of 14. I know it seems like I'm kind of skimming over that. In part, it's because what we actually do with this is slightly different. So let's look at how we actually use this. So you remember that Bohr said that there are energy levels, right? And he said that the first energy level held 2 electrons. Well, what we now know is that that first energy level of the electron, of the atom, excuse me, has one s orbital that can hold up to 2 electrons. So what do we mean by that? Well, that first energy level has an s orbital, right? The s. And we say that because that s orbital is on the first energy level, we put a 1. And because it holds 2 electrons, we put a superscript of 2. And what this means is the s orbital on the first level holds 2 electrons. Now, on the second energy level, we have another s orbital. And that s orbital is on the second level, so we put a 2 in front of it. It still holds 2 electrons. The s orbital can hold no more than 2 total electrons. On the second level, we do add the p orbitals. Because they're on the second level, we put a 2 in front of them. And the p orbitals, do you remember from your prior slide how many electrons they can hold? They can hold up to 6. So these numbers up here, these superscripts, are just how many electrons can fit in those orbitals. So this first energy level can hold up to 2 electrons. That little E with the line over it is an abbreviation for electrons. And how many can the second level hold? 2 plus 6. It can hold up to 8 electrons. Now, the third level still has an s orbital. Because it's on the third level, we put a 3 in front of it. The s's never hold any more than how many? 2. It has a p orbital, which can hold up to 6. And then we add the third type of orbital, the d orbital. Remember that atoms are 3-dimensional, right? So that first level is right in tight where the 3 axes intersect, if you think of it 3-dimensionally. So as you're coming out on energy levels, you have more space and more space because you're getting further from the nucleus. So 3-dimensionally, there's more room for orbitals. So the d orbitals, do you remember how many those can hold? They can hold up to 10. So remember, these superscripts are our electrons. So 2 plus 6 is 8 plus 10 more. That means this level can hold 18. On the fourth level, we still have the S. Remember, the number in front indicates the level it's on. So this is the S on the fourth level, can still only hold 2. The P on the fourth level can still only hold 6. The D on the 10th level is limited to 10. And now we're going to add our last orbital type, the F. Notice that my electron numbers are always jumping by what? 4 more electrons, just to kind of one of those clues to help you get in your head what these numbers are. When I add these superscripts up, which represent my electrons, this level now fits 32. What do you notice happens on the 5th level? Well, you'll notice that it still has all 4 orbitals. And then on the 6th level, it loses one, right? Scientists aren't really sure why that happens. It's a lot of times in chemistry and in science, we describe what we observe. We don't always have an answer for what we observe. So for some reason, we start losing those biggest orbitals on our 6th and 7th level. So whereas Bohr said that levels from the 4th out can hold 32, that's really only true for the 4th and 5th level. They hold 32, then we drop back to 18, and then we drop back to 8. What's interesting is if you look at the periodic table, our largest element that has been discovered or actually synthesized is 118. That's OG, if you look at the new periodic table. And so that one ends at 7p6 because it has all of these filled. So how do we use this? How are we actually going to apply this? Well, we're going to apply this through something called electron configurations. Let's look at what they look like. So I'm going to write these down. We're going to look at hydrogen, helium, lithium, beryllium, boron, fluorine, silicon, and argon. So let's go here. So remember that we said on the very first energy level, we simply have that 1s orbital, and it can hold up to 2 electrons. So the first thing we need to do is we need to look at the periodic table and determine our number of electrons. So if we look at hydrogen, right? Hydrogen has an atomic number of 1. That means it has 1 proton, and it also means that it has 1 electron. For these, we're focusing on electrons. So hydrogen has 1 electron. I'm just going to write the 1 there to remind myself. Let's go ahead and get our other ones. Helium is our second smallest. It has 2. Lithium has 3. Beryllium has 4. Boron has 5. And then we jump up to fluorine, which has an atomic number of 9, so 9 electrons. Silicon has 14, and argon has 18. So what happens initially is that for the smallest atoms, we just start filling in the energy levels. So hydrogen has 1 electron. So that means that it's going to start filling in the first level. So it's going to fill in the 1s orbital. But does it have 2 electrons? No, it only has 1. So it's going to put that 1 electron there. So this would be called the electron configuration of hydrogen. Helium has 2 electrons. So if you look at its first level, it's still going to start at the 1s. They're just filling them in order, at least initially. But since it has 2 electrons, it's going to put the electron also in that s orbital, but it can fill it up. So here's our first energy level. Hydrogen, helium. The hydrogen has 1 electron that it puts in the s orbital, so 1s1. Helium has 2, so it puts 2 electrons in there. If you look at the periodic table, what you'll see is hydrogen and helium are your first row, right? So this represents that first energy level, 1s1, 1s2. So let's go to lithium. We already looked on the periodic table. Lithium is the 3rd element with an atomic number of 3, so it has 3 electrons. So once again, it's going to start by filling in that first s orbital, 1s2. Now, once it's done that, I've used up 2 of my 3 electrons. And you know what? There's no more orbitals on the first level. So it's now going to start filling in the second level. So what's the first orbital we come to? 2s. So how many more electrons does lithium have? Well, it's got a total of 3. We've used 2. So it has 1 more that it can put there. Notice I'm just filling these levels in order. So if I've done this correctly, my superscripts, I know we want to call them exponents, but these aren't raised to a power, they're just superscripts, represent my electrons. So 2 plus 1, I've used 3 electrons, which is what lithium has. So look at beryllium. Take a second and see if you can, in your own mind, reason out what beryllium will do. Once again, beryllium has an atomic number of 4, so it has 4 electrons. So it's going to fill in its first energy first, 1s2. We've used up 2 electrons. And next, it'll fill in that s orbital on the second level, so 2s2. How can I tell if this is right? Well, I am filling them in order, and my superscripts add up to 4, which is the number of electrons beryllium has. Sorry, this is kind of slow, but it probably also feels kind of fast. Boron has 5 electrons. So once again, we're going to fill in the first level first, 1s2. Then we'll start filling in the second level, 2s2. How many electrons have I used up so far? 4. So how many do I have left? 1. So what's my next orbital to start filling in? The 2p orbitals. So I filled in my 1s2, my 2s2. Now I'm going to start filling in my 2p. But how many electrons do I have to place in it? Well, it can hold up to 6, but 2 plus 2 is 4. I've only got 1 more. So this will be 2p1. So let's jump ahead a little. Fluorine has 9. I'm just going to fill in the levels in order. So I'm going to fill in my 1s orbital first and use 2 electrons. My 2s orbital second. I've now used a total of 4 electrons. And then take a second and think, how many electrons will I have to put in that p orbital in order to have the right number of electrons? I had 9. I've used how many? So how many are going to go in the second p orbital? Well, 2 plus 2 is 4. What will I have to get to 9? 5. So notice that what we're doing is we're completely filling in the lower orbitals, and then in the last orbital that we get to, we're only putting in as many as we need. So make a big jump here. Silicon has 14. So let's look at our orders. I'm going to fill in my 1s2 first, my 2s2 second. If I fill in my 2p6, I'm at 2, 4 plus 6 is 10. So I still need to keep going. So what do we do after we fill in the second level? We go to the third level. We're just filling them in order. So my next orbital was going to be the 3s2. So now I'm at 2, 4, 10, 12, right? So next I will go to 3p. How many if I'm at 12, how many will I need to put in 3p to end up at 14? 2 more. Notice, just to reiterate, I fill in every orbital to its max. So for s's, that's 2. For p's, that's 6. Once I get to d's and f's, the d's will be 10, the f's will be 14. I fill in every orbital to the max until I get to the last one. And then I only put in as many as I need to get to my correct total for that element. So 2, 4, 10, 12, 14. This would be the electron configuration for silicon. The last one we're going to look at for now is argon, because after that it gets a little messy. So once again, we're going to start out with my 1s orbital. I've used 2. My 2s orbital will take me to 4. My 2p orbital, if I fill it all the way up to 6, will take me to 10. Now I'll come to my 3s, takes me to 12. And 3p, if I got 12, how many more do I need to get to 18? 6. So argon is the last one that is simple. And by simple, I mean it just fills the orbitals in directly in order. For some reason, and once again, scientists are better at describing and proposing reasons than they are for actually providing reasons. For some reason, the next orbital that's filled in after 3p6 is not 3d10. Instead, it jumps up to 4s2. So for example, after argon, our next element is potassium. So it indeed fills in the 1s2, 2s2, 2p6, 3s2, 3p6. That takes me to 18. But then instead of going to 3d10, it fills in 4s with 1 to get to 19. Oh, why does it do that? Well, scientists think that for some reason, an atom is more stable with electrons in the s orbital of the next level rather than putting it in the d orbital of the prior. Don't worry, you're not going to have to explain that. We do actually know the exact order in which the orbitals are filled. So what I'm going to have you do now is take a second and copy that order. You can see here I'm kind of reiterating that after argon, things get a little wonky. Instead of filling in the D, it goes up to fill in the S of the next level. And the same thing happens with P's. They fill prior to F's. But this is the actual order you will need to copy. Let me make sure this is actually correct for a second. So take a second and copy this at the top of a clean sheet of paper. We're going to use it to complete atomic theory number 2. I'm going to start working with you now at this point so we can do a few more together and we can talk about the process. But do copy this order right here. This is actually the order that the electrons fill the orbitals. Make sure you copy it in order, double check it, and then we're going to try some together. So thank you. Hopefully once we get back together, I can answer any questions and I can model a few more of these for you as we get to the bigger atoms. Remember that if you get confused, I'm going to have this in Canvas, so you can at any point come back and re-watch it.